So this talk was originally titled How to Use PL Theory to Make People Happier. While I was working on the slides, I decided to be a bit more direct with the title. So welcome to PL Theory for Unfucking Interfaces. We're going to talk about using PL design methodology to address UI design problems. UI in this case meaning anything that a user interacts with, so both textual interfaces and graphical interfaces. My name is Sig. For those of you who've never seen one of my talks before, I always do my slides in Blender. This time, I built a little art gallery around them. So we're going to take a nice stroll through this gallery. So what is a language? In this talk, I'm going to be using a fairly wide definition of a language, not necessarily something with a formal interpreter, but something with semantics and syntax and a relationship between those two. Something that could be formalized, but may not necessarily be formalized already. So lots of interfaces fall within this definition of a language. Anything that has modality or state that you can manipulate with buttons has, in this sense, a syntax, which is the interface, and semantics, which is the state that gets manipulated. There are lots of ways, and a simple interface can become language-like and grow in complexity. The most common is just that the role of the interface expands. As new features are added to some interface or configuration file format, it grows in semantic complexity and starts to more and more approximate a language, as well as its effects over the external program that it operates with increase. However, an interface can also become more language-like without increasing its effects or its syntax if its internal state expands fairly wide. This is pretty common when an interface is over-engineered or designed for programmers or something similar. As well, many interfaces become language-like through terrible accidents. Just mistakes in implementation, or looks like I've got a bit of mic feedback. I'm going to step back here.
The mic has a volume button which you can push down.
I won't worry about it. Plenty of things become accidentally Turing complete. So in this talk, we're going to be thinking like a PL designer for UI problems. So on the left here is the normal perspective that most people take when dealing with UI problems, and the right is the perspective that I'm going to try to introduce. So when we do something like parse a config file, in this mindset, we're going to be considering interpreting a program in the language defined by that configuration. As well, when we do something simple like adding a button to an interface, we're expanding the syntax of the language of that interface and adding more options for composing things together. If we add modality to an interface, we increase its semantics, or its semantic complexity, rather. When we validate input or check a configuration file against a schema, we're doing static analysis or something similar to syntax checking. As well, when we think about a user, we're not going to consider things like what would a user reasonably do. In this case, a user is a highly advanced fuzzing program that does anything it possibly can, and we want to restrict its options as much as possible. So language complexity is not something you normally think about with just a graphical application or something like that. But in this model, the complexity of a language has quite a lot of consequences for the design and usability or performance of a UI, and certainly its security, especially with configuration files. If your configuration file for a program has a lot of semantic complexity and a lot of effects it can control, it's very difficult to guarantee that any valid input file in that configuration file format is not a malicious program. As well, if the expressivity or the relationship between the syntax. So say you have a small program that has advanced semantics. So in this case, expressivity could mean something like looping behavior, then you're just asking for a high-risk exploit. Performance is also pretty relevant to this perspective. When we have a user interface that has unchecked growth in any of the dimensions we talked about, it usually ends up taking much longer to evaluate or repaint the interface or something like that. As well, from the user perspective, a language that is accidentally complex or a UI that could be simple and is more expressive than it needs to be is frustrating. It's hard to learn, it's usually not tested very well, and it gives the feeling of being buggy. So, what kind of tools can we take from PL theory to application design or UI design? There's a basic process that I use within this perspective for addressing problems. The first thing is to look at if you have an existing problem, say you have an exploit or a security hole that you're trying to patch that is related to semantics, or you're trying to make a UI more performant, or you're trying to design something new that you want to be solid from the start. You always want to start by formalizing the problem. Not necessarily with a mathematical model, but at least looking at what you have existing and trying to build up a framework describing it as a language. In this case, that means classifying the complexity of either the behaviors you have or the behaviors you want, and describing them in terms of formal grammars or just the interactions between things and the complexity of those. After that, you want to do something similar with your solution. So if you have existing semantics that you're trying to fix a problem with, you want to restrict those. So going from the model you developed previously to something that more fits your needs. Or when developing something new, it's useful to go from the vague idea of the complexity you want to an actual map of interactions that follow those semantics. Useful tools in this case are, for restricting complexity, you can add a type system. In this case, I'm not talking about anything complex, just the general idea of restricting things by types. Actually, very useful tool for graphical user interface design, as we'll see later. And after that, always follow the model you've built, whether or not it's formal or just kind of haphazard hinting at formal in your implementation, so that you never stray from your complexity targets. So the next portions of this talk are going to be two different case studies of applying these techniques to interfaces. The first is sort of an example in jest, but these things do actually happen. We're going to be looking at a configuration file format that has a security hole and trying to patch it very thoroughly. So the premise here is that there's a config file. It's just like a JSON blob that's for some like consumer software company's authorization daemons that runs as root because Windows and has become part of a privilege escalation chain. The history is that this simple JSON file for configuration of this daemon was added a couple years ago. It was very simple at that time. It is no longer simple. It has had a number of features added to it. It's now responsible for scheduling events and dealing with edge cases of authorization failures and stuff like that. It has fallen upon you to prevent this small exploit from getting a cool exploit name and logo. So this is what the file looks like. It's pretty simple. It's a pattern you see actually fairly common in JSON-based configuration files. You have sort of just an array of things that are interpreted. Those are sort of a command language. They have names for the commands, some options, and then you may be surprised that this is fairly common, but chaining operations happens fairly frequently in JSON configuration files. I've seen this quite a few times. So in this case, and this is of course a fairly trivial example, we have a situation where nested commands or chained commands go so far that they bust the interpretation stack for the command language and just insert a very traditional shellcode. So what happened here? The file has become infected by a command language. A very semantically complicated language has arisen out of this file entirely naturally by no one's intentional decision, just by adding new features to this configuration file and aggregating authority on that file. This probably happened because it was just easy in someone's corporate development process to, instead of adding new configuration interfaces, just like filing a pull request for the thing that interprets this. It busts the stack not because parsing JSON is hard, but rather because the language that has grown inside of this JSON file is likely being interpreted in multiple places. So what are our priorities for fixing this? Well, this command language has become sort of a core component of the authorization daemon for quite a lot of consumer software. So we can't just get rid of it, even though that's the reasonable thing to do. However, the recursion component is just a haphazard thing that isn't necessary for the operation of this daemon. So we can remove that. And we want to preclude any bug in this class of bugs from ever happening again, because we're going to get fired if it does. It will be our fault twice. So how do we fix this problem? What we want to do is we want to take this informally defined language that happened by accident and formally define it. We want to take all of the components that interpret that language that has quite a lot of control over this application, move them into one spot and isolate them from the rest of the program. We never want to trust the interpreter. If the interpreter fails, the entire program should not enter a failure state where you could write arbitrary data onto the stack. We also want to restrict the semantics of this language. So we want to remove we want to entirely remove the ability to chain operations together. That's silly. And we want to make sure that all input programs fall within the restricted semantics that we apply. In this case, we're going to do schema checking, which for JSON really only gives you the option of enforcing the syntax of any emergent language. So after we do parsing and checking against the schema, we want to recurse through the tree. And before following any operations that this configuration file does, we want to make sure that nothing is recursed too far. We want to make sure that nothing has invalid names. We want to make sure that nothing even exceeds the complexity of any particular operation. So even if we allow in the future some composition of operations, we never want them to have multiple compositions, say. And you just do this by tree traversal. So the solution here was just sort of vague, hinting at what to do. But the important perspective to take from this is what to do when you have an emergent language, something that happened completely by accident. The first thing you should always consider is just burning it. Accidental languages are bad. However, you can't always do that. When a language emerges out of certainly a configuration file by accident, it's often something that will take a year or so of corporate infighting to get rid of. So instead, you should not trust it at all. You should box it away, hide it in the furthest corner of the code base you can, and make sure it cannot touch anything of value. As well, you always want to take a language theoretic approach to problems of this particular sort. In this case, we could have also just secured the file. It's just one single JSON blob. Surely securing one file is not that hard. You never want to trust a file system's permission model for preventing a class of attacks related to arbitrary input. the permission model, certainly for most commonly used operating system, changes frequently and often without warning. Okay, so that was the first example. Our second example is a little more concrete. We're going to design from scratch a graphical user interface for some simple geospatial analysis. The premise here is that we have a large data set that's something like tracking cargo trucks or cargo planes, the things that are on them, and like location tags over time. And we want to make this data accessible for a normal person. Someone who is certainly not a programmer is much more comfortable with a spreadsheet-like interface or like Microsoft Office or just a friendly program than, say, I don't know if you can read this, that's a Python terminal. Their main responsibilities are not to write code or anything of the sort. They just write reports and do a little bit of analysis to show their managers or whoever makes decisions. And they don't care about programming in the slightest. If we're going to give them something with language like semantics, we need to hide it. So the purpose of the interface is just to help a person build very simple prediction models. In this case, these models are not programs. They're not even like R code. They're just sort of statistical plots in like a Microsoft Word document. We're going to assist in debugging those models. So if a manager reviews one of those reports and sees that it doesn't actually match up with the traffic of cargo or the prices of cargo over a particular span of time, we're going to show them that narrow bit of information related to that failure. And we're going to help analysts find unusual items. Say we're selling this analysis product to law enforcement, and we want to make a lot more money by helping them find things that are going in the wrong direction. So we've got a couple options for doing this. We've got a large data set, and we want to filter it. The option we're going to explore is making a small DSL, very restricted in semantics, and with a nice presentation for allowing them to put together filters and very simple analysis. The main challenge with this is versus other options, you end up with more of a design effort, and you often need to bring in more people within a team to make decisions relating to designing a language. There are other options. We could just embed SQL. That's pretty rude, and it also has a lot of problems. Sandboxing and making sure you set performance bounds on any embedded query language is also always a challenge. We could re-implement a user interface that the user is familiar with. We could just make a spreadsheet. The main problem with this is, as many companies have discovered within the last couple of years, when you re-implement Excel, you disappoint Excel users. Whenever they look for a feature that they commonly use within their workflow and they don't find it, they stop using your application. As well, we could just give the nerds CSV export. Anyone who cares about doing analysis on data can just take the data and do the analysis on it however they want. The main downside of this is that you cannot sell a product that does that. You can make a lot more money right now by presenting a half-assed user interface for doing analysis over a large data set than something reasonable like building a small component that just gives you that data. So we're going to go the DSL approach. What do we want? We want a friendly interface for normal people who don't like programming. Friendly here means that they're going to be doing some programming, but they're not going to think that they're doing it. That's the goal here. We want to provide them options for doing highly granular filtering, basically the same kind of features, or quite a lot of the features you could do with a SQL query, just behind a pretty interface. We want to give them some simple analysis tools. So we want them to be able to take the things that they've queried and do like distribution plots, find averages, find median trajectories of vehicles and things like that. And we want this interface or this language that we're designing to be very easily convertible to the things that actually execute. What do we not want? We don't want it to take very long to evaluate. We're going to be doing data analysis in JavaScript client side. So most of the things we should only allow a user to do things that we can evaluate quickly. We should only allow a user to ask for things that we can query quickly from a database. We want to restrict data transfer as much as possible for basically the same reason. And we want to prevent frequent recalculation and repaints. So we want our interface to be as static as possible. How are we going to do this? So the semantics of the language that I proposed here as a solution is centered on selections, similar to queries. We want to give the user the ability to take the whole data and pick a set out of that or pick multiple sets out of that. We want some ability for reference, so a set can narrow from another set, or a set can be a conjunction of two sets. We, however, don't want any recursion in selection. We only want essentially conjunction and narrowing. There should always be a fundamental limit to how much we can reference one set from another. And we want a very strict separation of operations. The operations for selecting data should be both visually and semantically distinct from operations that do analysis on that data. On the interface side, we want a fairly complicated syntax for selecting data because we want granular filtering of quite a big set of information. But we want it to be unambiguous so that the user never feels like they're doing programming. They never feel like they're dealing with a syntax, and they're never actually interacting with the language. We want to guide their selections of things as much as possible to narrow down the options of what we have to actually evaluate. And we want the interface to be self-explanatory, so they're thinking about it as little as possible. One of the best ways we can achieve most of these goals is by adding a very simple type system to the things we care about. In this case, this type system is essentially just a set of enumerations of the different types of data we care about. So we're not going to ever be doing any operations on strings. We're not going to ever care about the names of things even. We're only going to care about trucks, planes, cargoes, and prices. All of the analysis options are going to be restricted by types to only the things that we can do in an optimal fashion for those types. And all user interface options that are not type appropriate are just going to be completely elided. Okay, so I actually designed this. This is after fixing those principles and deciding on the PL theoretic approach to the UI design, there are some pretty obvious options for how to implement it. We want an unambiguous syntax, and we want the user to not have to think about the ordering of things at all. So we can just present our syntax as a tree. We have a hierarchy needed, so we just draw the hierarchy. This is fairly readable to people who don't want to or are afraid of programming. This is not something that looks like a computer program to an average user, even though it's fairly clearly a query. It's typed. The main aspect, or the first thing that is presented, rather, is the type of this expression, or this query expression. And it's very easily converted to a SQL query. All we care about is we have a type, and presumably we can select just from a single table because we've narrowed it to one type. and we only care about the property of its location and the time span it was at a location. So we have to reference very little. This is the reference semantics. The important thing here is that things are fairly visually self-explanatory. Set number 1 just does the same selection as before. Set number 2 takes a reference to set number 1 and narrows it down with an extra query layer. The naming of things is automatic in this UI, so they're only ever referred to by numbers and colors. The relationships between things are very obvious. The colors are always represented. The sets each have their own outputs. In this map, it's just the markers of things. And it's very easy to distinguish which set which output came from. Only subsets and conjunctions are allowed for referencing, and we automatically order things by their dependencies. So you can just read this filter list from the top to the bottom. This is what an analysis output looks like in this UI. This was a pretty unambiguous decision. Just take a reference to a set and do some very simple implicit operation on it. In this case, we're just analyzing frequency of things near the airport in the last 20 minutes. The bars here are also just implicit. The important thing about this UI design is just preventing the user from making as many decisions on behalf of the user as possible, which allows a person to think much less about the semantics they're working with. I'm not sure how much of this you can see. This is the sort of an example of how to interact with this. There's just a plus button below. You click it, you add something. The first thing you pick is the type of the expression. The second thing you pick is the type of the data you're going to be operating with. And then you add extra filter queries to it. By doing this, we prevent the user from ever creating very complex queries. We start from just a simple set of operations, and we only ever present a simple list of options. And we end up with something that we can evaluate quickly and that the user can understand simply. OK. So that was the second example. This is my takeaway section. The thing I wanted to demonstrate here was that anything can become a language. Things can become accidentally Turing complete. Things can become accidentally recursive in plenty of situations. But even if it has not become language, like pretending that things are can be very useful. Starting with the assumption that you're going to be working with a fairly complex set of semantics is often a much more useful perspective than, say, starting with the user interface interactions or the just behaviors or maps or like sketches of an interface. It gives you a much better foundation to start with when designing something. You should care about formal complexity. Not in the sense of you should always create a formal model for your interfaces, but instead know that there are consequences to making things too complex. Please stop making things Turing complete by accident. And now I'll take questions.
So suppose here that you're working like with different teams, designing the UI and implementing the sort of this idea. So do you have any idea of how easy it is, to sort of model this together? Because I get that maybe the UI people might not be as used to this PL approach that maybe are.
The intent of this talk was actually to be at least slightly convincing to UI people. They're the team that is usually most authoritative for this kind of decision. Not for, say, configuration files, but for graphical user interfaces, certainly. This is something that I think UI designers need to think about more. I don't particularly think it's a good idea to try and have engineers or, say, the one functional programming advocate on a team on an application team to try and convince the UI designers to take a very formal approach. But instead, it would be much, much nicer if UI designers knew about the complexity of the things that they were putting together from the perspective of semantics, not just from complexity of user experience or complexity of visual noise or stuff like that.
Can I interest you in giving this talk again in next year's LangSec workshop?
Sure. I'll try to make a more solid example
Thank you.
for the security aspects.
Is there a way to verify that something has not accidentally become a Turing language?
If you create a formal model of the semantics of something, you can then go from that formal model and attempt to satisfy the bisimulation condition with a Turing machine. If you cannot, then it is not Turing complete.
So for the second example that you went to, did you actually start with the formal model?
What I did for designing this is I fixed the setup principles that I introduced in the section right before. I made a little bit of, not a totally formal model. I didn't make like an actual mathematical thing. I didn't write any like proofs. But I wrote down some example transformations between textual syntax for this and SQL and JavaScript. And I narrowed down the edge cases as much as possible, thinking from the formal perspective.
Do you have any experience or is there any advice you have, I guess, for safely creating emerging languages? Like, can you subset what they can do in such a way that you preserve, I don't know, domain knowledge and intent, things like that?
That's a pretty interesting question. So like, I'm going to interpret it as like, if you're working on a team and you're afraid that an emergent language is going to come out of something you're working on, what can you do to restrict its damage? The best thing I think in that circumstance is to preempt the accidental language by creating an intentional language that has semantics restricted to the point you want. It's very difficult to control something that just grows on its own. Yes?
So how do you take one that already exists, that already has like a lot of stuff that depends on it, and try to restrict semantics in a way that you make something that's actually usable? Like I can't get rid of it, I can't fire it, but how do I make it, not completely insane?
Usually you want to strip features away from it one by one. You want to start with, you want to do as much refactoring in the code base as possible to make sure that it's obvious where the interpretation of this language happens. And you want to take that interpreter and remove features until you reach the minimum useful subset of that language. It is not the most common case that every feature of the semantics of this language is critically dependent upon. There's usually something that was just added haphazardly that is the cause of the complexity problem that you can get rid of. Yes?
Say we had a web form, or any GUI, for that matter, which had grown to be overly complex, and had weird states if you went through a certain sequence. Is there any tools, either formal programs or just style of charts you like to draw that would aid in recognizing it in a more programmatic kind of manner and documenting those states and things like that?
So the question was, if you've got a user interface or a graphical user interface that has become semantically complex, what tools can you use to map out the semantics of that? The most important, I think, is just drawing a graph of the relationships between user interface components to each other. Not necessarily anything formal, just starting from all of, like if you click this button, what other states of the user interface could you affect? Going from that and collapsing it down to a semantics of each button is an operation within a language, and what states do you need to model the interactions between those things, what internal states. And you can then go from there if you wanted to go to a completely formal model and make a TLA plus proof of the interactions of those. Yes?
How would you begin to incorporate principles of affordance and wayfinding into something like a DSL?
I feel like the language perspective does not really cover those kind of concerns. Instead, you don't want to just take or in the user interface case, you don't want to just take the design approach of restricting complexity as much as possible, as I introduced here. You have to match that with the other approach of making it actually usable. But the language theoretic approach is very useful for making sure you don't end up with edge cases. Yes?
Are there, is there writing that like explores this idea of mapping user interfaces to graphs of them, etc.?
There's actually quite a lot of research, not in that direction, but in the other direction of PL designer types trying to design user interfaces that behave like programming languages. I'd be more than happy to recommend a few of those after finishing questions. Any others? Guess not. Oh, one.
Yeah, I just thought of one. Well, I was interested if you remembered any edge cases that you encountered while you were designing the second example.
So one of the things I bumped into that made me add extra typing or restricting typing further than I had started with for the data types was I'd initially included an example of doing an analysis of the transitions of cargo from one type of vehicle to another. And I ended up not being able to assert and prove that I could evaluate that kind of analysis without having I'm not sure what the word is. I'm just going to say octratic evaluation time complexity. There was no way to restrict the relationships between those two things in a way that I could actually run in JavaScript, basically.
That was a transition from like a car to a truck over?
From a plane to a truck was the example here. I was using my hometown, Austin, which doesn't really have ships. So those are the only two relevant types. Okay. If there are no other questions. Thank you for visiting my art gallery.